So what is Cartesian representation? Well, Cartesian representation is written in a way so that you can write a vector in terms of unit vectors along some fixed canonical directions. So what you do is you pick two directions that are perpendicular to each other. Why perpendicular to each other? Because you want them to be independent of each other. And perpendicularity implies that that two things are independent of each other, right? So what you do is you pick two perpendicular directions. We'll call them x and y, okay? And what we will do is we will try to write this vector in terms of the vectors that go along x and y direction. Okay, and this is called vector law of triangle. So I can write any vector as addition of any number of vectors. Any vector can be written in terms of addition of any number of vectors. Here, because this vector is in a plane, which we are calling xy plane, I can write this vector in terms of two vectors that go along x direction and y direction, right? It's almost like saying that, you know what, here, this is a problem for you. You are here and you have to get over here, okay? And you are not allowed to travel along any direction except for horizontal and vertical, okay? So how do you get over here then? Well, you're only allowed to travel along horizontal and vertical direction, so you can go this way, and then you can go that way, and you will get there, right? Is that the only way you can get there? No, you could go up first, and then go towards the right, and you will still get over there. And all of these would be same. There will be no difference. Why they won't be any different? Because if you go up this way, you are basically traveling along a vector, which will be same as this. If you go this way, you'll be traveling along this vector, which will be same as this. Why? Because both the vectors have the same length and same direction. They're free vectors, so you can move them anywhere you want, and nothing is going to change about them, right? Now, if I said that, hey, you're not allowed, you can only travel along perpendicular directions, will this be the only choice available to you? So I'm relaxing the problem a little bit for you. So I'm saying that I want you to go from here to here, and you can pick your perpendicular directions. Will this be the only choice for perpendicular directions? Yes? No? No? What other choices can you take? Well, there are infinite number of possibilities, right? What you could do is you could say, hey, I'm going to pick this as my, perpendicular direction. I could say, this is my one direction. Let's call it x prime, and that's my other. And these two are perpendicular too. So to get from here, this is the origin, to the destination, I could go this way first. I could go this way first, and then I could go perpendicular that, like that. And I will get to the same destination, right? So when I pick these two as perpendicular directions, essentially I picked a different reference frame. Now, choice of reference frame is completely arbitrary. It isn't any different from picking maybe a certain unit system to express a quantity, right? You could express your mass in kilogram, in slugs, in pound mass. These are all relative. As long as you specify the unit system, people will know what you're saying, right? So if somebody wanted to really compare your mass with theirs, because that other person feels comfortable with maybe a size system, and you specified your mass in USCS, he or she could do the conversion to really meaningfully compare the two numbers, right? So the choice of coordinate system is completely arbitrary. Just because we show x and y like this doesn't mean that those are the only possible directions available to you. As long as you pick two perpendicular directions in the plane, you're fine. And you will see pretty soon in what situation picking maybe an alternate set of perpendicular directions to draw your vectors, to show your vectors, would be beneficial, right? So, okay, coming back to the Cartesian representation. So this is our vector. These are our canonical directions, x and y, right? So I can write this vector as a sum of this vector plus this vector. Now, we already know that any vector can be written as the magnitude of that vector times a unit vector along that direction. That's what we learned in the previous slide. Okay, so what we need to do is we need to specify what our directions are along x and y. Okay, and how do we specify the direction? By writing the unit vectors. So let's say unit vector along x direction is I hat, and along y direction is j hat. So in a three-dimensional coordinate system, you also have z-axis. Along z-axis, the unit vector is usually written as k hat. Okay, so I hat is a unit vector along x direction, j hat is a unit vector along y direction. So now I can write v1 and v2 easily, because I already have assumed the unit vector along those directions. v1 would be the length of this. And what is the length of this? well, we have to do a little bit of trigonometry. This is a right angle triangle. This is 55, so this will be 55 cosine theta. So the vector v1 becomes 55 cosine theta I hat, and v2 becomes, which is this, 55 sine theta times j hat. Right? So those are the two vectors, and now I can write this vector v as sum of those two. So when I do that, this is what I get. So 55 cosine theta and 55 sine theta are called the Cartesian components of this vector. So Cartesian components are essentially nothing but the x and y components. Okay? So you have to pick your x and y direction, and then you can write your Cartesian components. So this is called a Cartesian representation. So given any vector, whether it's a velocity, acceleration, or force, if you know its direction and magnitude, all you have to do is do a little bit of trigonometry, drop the perpendiculars from the tip to the x and y direction, look at these lengths, direction you're moving in, and you got your Cartesian components. Right? Okay. So let's look at an example. So we have already written v in polar representation as this, and v in Cartesian representation this. Both of them are same vectors, so they have to be same. So if we compare, you can see that the unit vector actually is nothing but cosine theta I hat plus sine theta j hat. Right? So that's the unit vector. Now, could you have written that directly after you learned about Cartesian representation? Sure. You know that this is the unit vector along this direction. The unit vector has magnitude as 1. So if you drop the perpendiculars, you'll get cosine theta here and sine theta over here, right? So let me draw this. And I'm going to do it separately over here to illustrate. So this is my velocity vector, and I'm just showing a unit vector, right? So you can see its length is small because it's unit magnitude, right? And this angle is theta. So if I drop the perpendicular, this would be equal to cosine theta, and this would be equal to sine theta. Why? Because the length along the diagonal is 1, right? So it's 1 times cosine theta and 1 times sine theta. So now I can write E hat directly from here as cosine theta I hat. Why? Because this is E hat, and these are the directions, plus sine theta j hat. Right? This angle is theta over here. So once you know the Cartesian representation, it doesn't matter whether a vector is a unit vector or not unit vector. You can always drop the perpendiculars and write that. Right? Okay. So let's look at another example. We have a force, which is also a vector, that's shown as of 5 Newton at an angle theta from negative x-axis. Right? So this is positive x-axis, this is negative x-axis, this is positive y-axis, this is negative y-axis. Right? Okay. So if this is negative x-axis, then this vector is opposite to this vector x. So if you have a unit vector pointing that way as I hat, then the unit vector pointing other way would be minus I hat. If this is positive j hat direction, then the opposite way would be minus j hat direction. So if I want to write this vector, how can I do that? All I have to do is find a way to get to the tip, right? And there are more than one ways. So I can go in the negative x direction like this, and then go in the positive y direction like that, and I can write f as sum of f1 and f2. Okay? So what is f1? f1 is nothing but 5 times cosine theta, that's the length, and this direction is negative I hat. So f1 is f cosine theta times minus I hat, and f2 is 5 sine theta plus j hat, right? That's the positive j hat direction. So you add them together, and you get your force F. Now, absolutely everyone in this class should be able to write any vector shown graphically like this in terms of Cartesian components. Okay? And that's not something that anybody could say, hey, I didn't learn this in Mech 101.